So developers today, in all major programming languages, make extensive use of third-party packages. These are packages developed by other developers and available for download from several online repositories. To give you an idea of what's been going on lately, here I plot the number of packages over several package repositories, and you can see that we're on the order of hundreds of thousands of packages from tens of thousands of different authors. This line over there, the spike is JavaScript, and you can see that lately there has been a shift towards this model of development. And although this is great in terms of software engineering, the fact that we can develop faster, we can ship code faster, this is extremely dangerous for end users. There are many reasons for this. I'll just cover a few of them. First of all these packages are on the order of tens of thousands of lines of code, which means that understanding or verifying what a package does or doesn't do is extremely difficult, especially when we're talking about dynamic programming languages with no static annotations, no type annotations or anything. Due to recursive imports now, since these packages import other packages, we're talking about applications with hundreds to thousands of other packages. And due to the popularity of some of these packages, an attacker can very easily plant a vulnerability, an attack into one of these packages and have widespread impact. We saw this with leftpad and other packages that are depended upon by tens of thousands of other applications. Okay, this is the core problem, and we're not the first to identify the problem. Actually, there are a lot of companies out there who spend a lot of effort and investment in trying to solve this problem. And what they do usually, I mean, there are a lot of ideas, but what they do is pay people to inspect the source code and verify the absence of problems. Of course, this doesn't work in practice, and this is why we have all these issues. Our idea is a little bit different, and here I'll explain what it is. Generally, we take advantage of a really old idea in computer security, which is this idea of compartmentalization, taking an application and decomposing it into smaller compartments that do not require less privilege than the overall application. Okay? Just to give you the core idea, if there's only one slide you're going to remember from this talk, I want it to be this one. Essentially, we put individual modules into their own compartments. We can think of compartments as processes for now, but later on I will describe different types of compartments. So today, your operating system starts an application in its own process in order to make sure it doesn't mess up with the internal state of other processes. This is one of the reasons. And this security architecture was designed at the time when people realized that different applications would be built by different developers. So we didn't want applications to mess up with each other's state. But today, as I described earlier, we're talking about individual applications being developed by multiple third-party developers and even individual modules within these applications. So the core idea, as I said, is to put modules into their own compartments and want to do this automatically. So we have a set of automated transformations that spawn individual modules into their own compartments and maintain the illusion of while maintaining the illusion of a single runtime. So this is a special case of a distributed system in some sense. Now, the second idea is this giving the flexibility to developers to disable which of the features of the programming language that come by default, such as global variables or accessing the cache of the loaded modules at the module boundary. So each individual module gets all the access it needs to the language features, but at the module boundary, you might want to disable some of these features. Okay? Let me explain this with an example. So here I have a blogging platform, the idea of a blogging platform written in JavaScript, which is essentially a function that takes request objects and populates response objects. Our developer here has imported, this is in JavaScript, a few packages. First, the database configuration file, which is private sensitive data, EJS for template rendering, and Minimatch which is a small matching library. Now, it is known that certain versions of EJS today are susceptible to remote code execution, which means that third-party, attacker code running through EJS can actually access the database configuration file through a number of different ways, through features that are by default enabled in the programming language, okay? For example, they can read the global variables, or they can poison the prototype chain, since we're talking about a prototype-based programming language, or they can access the cache overload modules, today runtimes, cache modules, both for consistency and performance, or you can just import the built-in file system module and just access the file system directly, okay? Nothing. And these are valid, these are valid actions at the level of the application as a whole, right? But you might not want this module to have access to these features. Now, Minimatch is known to be susceptible to denial of service attacks, which means that being fed pathological regular globe expressions that will be converted to regular expressions, it can actually freeze the application, okay? And when we're talking about applications built around a cooperatively scheduled concurrency model, this can be really, really painful. Okay, the first idea I described is this idea of automated transformations. What do? Okay, we import our tool BreakApp there that essentially the idea is change what the import statements do. So instead of just reaching into the file system and bringing some code to the current compartment, they spawn a new compartment and set up a channel between the parent compartment and the child compartment. Now, the second idea is using a bunch of other transformations to maintain, as I said, the illusion of a single runtime. The application needs to keep thinking that it's running in a single compartment. And there are many technical, a lot of transformations we described in the paper, one of which is transforming function calls to remote procedure calls that will ship arguments to the remote compartment, will run the function there, and ship results back to the parent compartment, okay? Let's see, using the same exact module with the same vulnerabilities, EJS now does not have access to global variables. It's a completely different address space. It cannot poison the prototype chain. It can still poison the prototype chain, but it will only poison its own prototype chain. It can only access itself from the cache overload modules. It won't be able to access any other modules. And if we have namespace access to the file system, for example, we won't even be able to access, to read the database configuration file. Now, Minimatch is still susceptible to denial of service attacks, which means that being fed pathological regular expressions, it will still block the event loop. But imagine this is a search capability of our blogging platform. The rest of the application will still be unaffected. So users will be able to post comments and posts and read other stuff. They will not be able to search, though. That's a problem. Later on, I will describe policies that allow you to replicate actually compartments and further mitigate denial of service attacks. Okay, I want to emphasize a couple of points. The import statements, generally the code remains the same. This is the core idea. There are no manual rewrites required. There are no tracing or inference pre-runs. This is mostly automated. The core idea, the core insight is that the developer has already specified the module boundaries through these import statements. They have already given us the information we need. Okay, the second idea I want to discuss is this idea of policies. So as I said, we don't want our module to access the cache overload modules, right? But what if, and most of these modules shouldn't, but what if the only reason you are importing this module X is to access or transform the cache overload modules? Sometimes you need to give some of these capabilities to third-party code, right? So we allow developers to specify explicitly what behaviors they allow at the module boundary through these policies. For example, here, the developer says that they want, as I said earlier, you can think of compartments as processes, but now I say it will be runtime sandboxes. But because the database configuration file is part of the trusted part of the application, you can still import this into the current compartment. You can spawn EJS and Minimatch in their own containers and processes, respectively, and share the database configuration file with Minimatch, a read-only copy of the database configuration file. So this affects essentially the transformations that I described earlier are actually transformation templates, and all these policies plug in and instantiate exactly how the transformations are going to transform your program. Okay? A couple of points on policies. Developers can specify policies at the top level, and these will propagate down the dependency chain. Or they can go at the level of individual modules at a very, very fine granularity and specify what behaviors they allow or disallow. A key property here is that there is no reliance on discovered malleabilities in the sense that you can have two different applications exactly with the same dependency chain, but because the trusted part of the application is different, the use of these modules is different, policies allow users to disable and enable or enable behaviors based on what they know about the trusted part, their part, the part they're building. They know why they're importing modules. And policies are backwards compatible, the expressions are backwards compatible with existing code bases, because, as I said, BreakApp will choose some default policies. And they are forward compatible with vanilla runtimes, which means that even if we go and annotate all of the code out there to increase security, it will still run on completely unmodified vanilla runtimes. Okay? So now I want to discuss a couple of points. There are more. There's more evaluation and results in the paper. The first is all the idea. The idea that I just described here is predicated upon the hypothesis that applications today make extensive use of third-party modules. Is this true? I mean, it is. I mean, several talks yesterday described that. I'm going to emphasize a point that's a little bit related to performance, like how many modules. We do, so at the top level, the sort of the direct level from the trusted part to the third-party code, we have on the order of it's a two-digit number, from 20 to 30, let's say. So this is the number of compartments we would need at the top level. Again, users with BreakApp, they can use policies to group larger numbers of modules together. Okay? Now, if we want to go a level deeper, then the number of compartments will jump by an order of magnitude, which might actually require insights in, I don't know, lighter weight operating system primitives or hardware mechanisms. Okay. Okay, another interesting, there are a lot more details in the paper that just that third-party code is an order or to 2 orders of magnitude larger than homegrown code, so which is, I found a little bit surprising. Okay, so what's the performance overhead? So here I plot a number of widely used modules with different characteristics and their latency of running a simple function. So the baseline is no compartmentalization. Sandboxes use sandboxes for compartment types or process and containers. Okay, and you can see that there's a considerable overhead, since in certain cases the function it's sort of comparing something with zero. It's as if it's infinitely more expensive. Okay. And this is true, but if we put this into perspective, into context, here I plot the same results, but now they're behind an HTTP server serving requests to a set of local clients co-located on the same hardware. And because we're already paying a lot of overhead, the overhead seems to be, the total overhead seems to be on between 10 to 20%, which is something that I would be okay paying, so that my native module written in C cannot forge pointers and read the database configuration file. Okay, even as a user, I mean, not as a researcher. Okay, does BreakApp mitigate any potential problems? I described in the examples earlier that it does. Here we have a set of the first part, real vulnerabilities, vulnerable packages, and then a set of hypothetical vulnerabilities that BreakApp mitigated. And the interesting thing is that a couple that were hypothetical at the time we submitted the paper were actually realized by the camera-ready version of the paper, which I found interesting. For example, people snooping sending your environmental variables to remote servers. Okay, a couple of key points that I won't take away, and then we can discuss. The first takeaway is that this opportunity that the way applications are built today, using many potentially dangerous third-party modules, although risky, it offers clear boundaries of trust. And there are multiple ways of taking advantage of this, one of which is this idea of automated compartmentalization. It's an old idea. We didn't know how to do fully automatically. And here, with knowing the boundaries exactly, we can do automated transformations and add these runtime policies that further automate other decisions to do automated compartmentalization. Looking into the future, I think this opens interesting avenues in terms of research. Sort of the direction we're looking at is, could we potentially make applications with many possibly dangerous third-party packages be safer than monolithic applications that were designed with security in mind? This is a sort of a provocative claim in the sense that, okay, the first thing we're showing is that you can retrofit, in some sense, security into existing systems that were not designed with security in mind. That's one thing. But because you can sort of distinguish between different behaviors at a very fine granularity, we could actually make them even more secure, I think. And this is the first step towards this direction. This is definitely not the last step, what I described here. Thank you very much.
Yes. Hi. Ben Schock from CISPA. Very interesting work. Two questions. First one is, so you talked a little bit about kind of as a vision that this could be somehow automated. How would you see to follow up on the previous question and the previous talk, on the usability of this now? Do you think this is something that can be deployed by developers?
Yeah, the automation part is mostly, it's a significant part of it is solved. I mean, it gives further, it gives a lot of automation there are a lot of things you can do further down the line. For example, you could automatically choose, you can imagine a future where you can automatically choose policies or infer policies, okay? But in terms of automation, I would say that it's a significant step forward. The question is, how does it perform in terms of performance? I think this is the big impediment for adoption, not automation.
Okay. And if there's time for another question?
Yeah.
So you made the example now of Node.js. I kind of have a, more like client-side, web security background. Yeah. So I'm thinking, do you think this is possible to also adopt on web applications, that is JavaScript in the browser? Because we know that there's third-party components that are typically break sites or add some malicious stuff to them. So do you think there's room for transferring this?
Yes. There has I think James Mickens was here yesterday at least. He has led a lot of work on client-side compartmentalization. The threat model there is a little bit different in the sense that on the server, we have native modules written in C that can forge pointers and do crazy stuff. They can call POSIX APIs. They can do anything. In some sense, on the web browser, you already have some safety, the guarantees of a high-level memory-safe programming language. Okay, sorry. Yeah. But I think not only can it be adapted, but in some sense has already been done partly, at least.
Okay, thank you.
All right, last paper of the session. We've got